Dear students, in the last class we discussed classical free electron theory. In that classical free electron theory, the electron gas is compared with that of the gas molecules, and by applying the kinetic theory of the gases to these free electrons, certain experimental facts were explained successfully, but few experimental facts were remained unexplained by that classical theory. The classical theory failed to explain certain experimental facts. So, the classical theory was modified by Sommerfeld, and that theory is quantum free electron theory. Here, in this theory, in quantum free electron theory, Sommerfeld assumed that the electrons follow the quantum statistics, and electrons also obey Pauli's exclusion principle. By using these things, he modified the classical theory and he gave the new theory, it is quantum free electron theory, and this theory could explain the experimental observed facts successfully. And in this quantum theory also assumes certain facts, few of them are same as that of the classical theory and few are added to that. The assumptions of the features of this quantum free electron theory are: the valence electrons are treated as the free electrons, and these free electrons are similar to, their behavior is similar to that of the gas molecules. They are equated with the gas molecules, and these free electrons, they are free to move everywhere inside the metal. Inside the metal they are free to move, and here they experience a potential due to the positive ions. And the potential experienced by the free electrons due to positive ions inside the metal is assumed to be constant everywhere inside the metal. And the potential due to mutual repulsion between the free electrons is assumed to be negligible, or it is considered as insignificant. And one more feature is, at room temperature, emission of electrons from the metal is not observed. Electrons are not free to come out of the metal at room temperature. For this, the expression given is, the potential, when the electron inside the metal, they experience less potential compared to the potential on the surface of the metal. So, the surface of the metal is considered as a region of higher potential, and it is treated as the potential barrier. The metal surface acts like a barrier so that electrons cannot come out. So that the electrons inside the metal are considered to be confined to a region called as the potential box. The potential box represented like this. Inside the metal is nothing but a potential box having a potential barrier. The surface is a barrier of height denoted as ES. Let ES be the height of this potential barrier, so that the electrons inside the metal, they cannot come out. This the metal is treated as a potential box wherein the free electrons are confined. These are the features, and one more feature is, electrons obey FD statistics, Fermi-Dirac statistics, whereas in classical theory it is assumed that the electrons obey MB statistics, Maxwell-Boltzmann statistics. MB statistics, also called as classical statistics. There, in that MB statistics, the energy of the electrons is assumed to be continuous. Electrons, they do not possess any spin. They do not obey Pauli's exclusion principle. So, Heisenberg's uncertainty principle is also not applicable in case of MB statistics. But in quantum free electron theory, Sommerfeld assumed that electrons follow FD statistics, Fermi-Dirac statistics. So, electrons, they possess half integral spin. So, the electrons are also called as Fermi ions. And these electrons, their energy is not continuous, it is quantized as per this quantum free electron theory. And one more feature is, electrons obey Pauli's exclusion principle. The distribution of electrons in different energy levels takes as per Pauli's exclusion principle. That means no two electrons can have the same energy state. They cannot occupy the same energy state if their features are identical. They can occupy the given energy. Two electrons can occupy a given energy state with opposite spin. One electron having spin up, other one having spin down. Such two electrons can occupy a given energy level. So that the energy levels are filled. The energy levels of the electrons in a metal are filled as per Pauli's exclusion principle. These are the features of quantum free electron theory. And in this theory, the facts which are unexplained by classical theory were explained successfully. Now let us consider some facts such as energy density of states. Say in a metal, the electrons are confined to that potential box. Then these electrons, they occupy different energy levels. Plenty of energy levels are available for electrons inside this metal. And those energy levels are very closely spaced and they form a group. The energy levels form a group and that group is called the energy band. So, energy of the electron is not having a single value. Instead, it spreads over the energy band. See, it is said that, in the theory it is said that in a volume of 1 mm cube, in volume 1 millimeter cube, in that volume of the material or that metal, in a given energy band, there are billions of energy levels. Billions of energy levels they form a group to form the energy band. The energy spread of the energy band is over few electron volt. Very few. This energy spreads over, or energy range is over a very few electron volt. And this is how the energy levels are grouped to form energy band. And the number of these energy levels in an energy band is explained, or it is denoted by the factor called as density of states. It is explained by the factor density of states or energy density of states. Energy density of states because these energy states are connected with the energy. There is a relationship between these energy levels, density of states with the energy. And that energy density of states, it is denoted by a function called density state function. G of E dE represents the density state function. This density state function gives us the idea about the energy distribution among different energy levels. The number of energy levels related with the energy. That relationship is given by this density state function, denoted as G of E dE. Here, G of E dE gives the idea of density of energy, density function for an energy range of dE, or the number of, it gives the idea about the number of energy levels spread in an energy range of E and E plus dE. This is nothing but G of dE given by this formula. It is G of E dE is 4 pi V by H cube 2n to the power 3 by 2 e to the power half dE. M, mass of the electron, V is the volume of that potential box or that metal, H Planck's constant. And this is the expression for the density state function. And this expression says the density state function varies with energy as root of E. Energy and the energy states are connected by this relation. And the variation of density function with energy is given by this. This is how the density states vary with the energy. Next is about the Fermi energy. In a metal, suppose there are n atoms. Then there we find n energy levels available for the electrons to occupy. If n is the number of energy states available for the electrons to occupy in that metal having a number of atoms, then the electrons occupy those energy levels by obeying Pauli's exclusion principle. And as we discussed here, the energy levels are grouped to form the energy band. So inside the potential, see, these are the energy levels which are very closely spaced. They form a band. It is here, see. This is the potential box. The energy levels are closely spaced, forming a band. Now, electrons occupy these levels by obeying Pauli's exclusion principle. In any energy level, it can be occupied by two electrons having one having spin up, other one having spin down. So that in this manner, the energy levels are occupied by the electrons from the lowest level. Lowest level, then the next one is filled. In that manner, the levels are, the filling up of the levels goes on up to a level where, which is the number of electrons there, suppose it is exhausted. See in this diagram, so this is the uppermost level which is filled with the electrons. Above that, all the levels are empty. This maximum level, this energy level, which is filled by electrons, is called as the Fermi level. This level is called as the Fermi level. And the highest energy level filled at absolute zero. The highest energy level filled at absolute zero is called as the Fermi energy, denoted as EF of 0. EF of 0 indicates the Fermi energy. It is nothing but the energy corresponding to the highest filled level. It is at absolute zero. At absolute zero, called the Fermi energy. And this Fermi energy is also nothing but the maximum kinetic energy of the electrons at absolute zero. This also gives the maximum kinetic energy of the free electrons at absolute zero. This is about Fermi energy. See, all the levels up to this Fermi level are completely filled, and above all are completely vacant or completely empty. And this is about the Fermi energy. Now, one more factor let us discuss. It is Fermi factor. Fermi factor, this factor is a function of energy. And this factor, this function explains the way how, explains the probability of distribution of the electrons in different energy levels in a band. Fermi factor explains the probability of distribution of electrons in different energy levels in a given band. Over that spread band at thermal equilibrium. That's very important. At a steady temperature or at thermal equilibrium, Fermi factor gives the probability of distribution of electrons in different energy levels. And this Fermi factor is given by this formula. F of E, nothing but 1 by e to the power E minus F by kT plus 1. Where K is Boltzmann constant, T the equilibrium temperature, steady temperature T, then EF is the Fermi energy. That depends on the temperature. At absolute zero, it is called the Fermi energy, EF of 0. Or it is the energy of here, energy corresponding to the maximum, highest filled level. And this is about the Fermi factor. The variation of Fermi factor with energy is as shown in this graph. The Fermi factor varies with the energy like this at a temperature T equal to 0 and temperature more than 0 Kelvin. See, at T equal to 0, at absolute temperature, at absolute 0, see all the levels up to EF. See, this is the energy axis. This is probability of occupying the energy levels. Highest probability means 1. So, this is the highest probability at absolute 0. Look at this graph. At absolute 0, all the levels up to this Fermi level are completely filled. 1 means completely filled. And above this EF, the levels are completely empty. There is a sudden drop. There is a sudden drop in the Fermi factor, F of E, at absolute 0, equal to 0. At T more than 0, what happens? At T above this 0 Kelvin, what happens is, see, look at this graph. A small tail appears in the graph. A small tail appears in the graph, and the graph says, see here, at T more than 0, the probability at this energy, EF, at the energy EF, that's the Fermi energy, at the Fermi energy is that energy. See, we can define Fermi energy at T more than 0 Kelvin as, it is that energy. Which one is half filled? The probability of filling of that energy level is half, 0.5. And slightly below EF, certain levels, see, are not completely filled. There is a decrease in the probability of occupation for energy ranges, slightly below EF, and slightly above are not completely empty, but that filling goes on decreasing. At a certain energy, the probability of occupation becomes completely 0. This is how the probability function or this Fermi factor probability function explains the variation of the probability of occupation with energy at temperature scale 0, absolute 0 as well as temperature greater than 0 Kelvin. This is about the Fermi factor. Now let us see some case of probability of occupation. The probability of occupation already it is very clear in this graph at different temperatures how the states are filled, what are the probabilities of occupation of the given energy levels. Still, consider case 1. Case 1 is T equal to 0 Kelvin, absolute 0. Suppose the energy of that particular level is less than the Fermi energy. When the energy of the level is less than the Fermi energy, then the probability function, this Fermi factor, here substitute T as 0. Substitute T as 0. See here E is less than EF. So this term becomes minus. T0 means this one becomes minus infinity. Plus 1. E power minus infinity, 1 by e power infinity, it is 1 by infinity 0. So that you get probability of this function f of e as 1. Indicating that all the levels below EF are completely filled. Already explained that probability of filling that occupying the energy state f of e is 1, indicating that all the levels below EF of 0 are completely filled. Case 2, T is 0 Kelvin. Suppose E is greater than EF, the level above that EF Fermi energy, the energy level above Fermi energy. What happens? See here, this term E minus EF becomes positive, T is 0, so this is e power infinity. E power infinity plus 1, so 1 by infinity. E power infinity is infinity, so 1 by infinity is 0. So what it says, all the levels above this Fermi level are completely empty, not filled at all. Third case is, suppose E is equal to EF. Case 3, E equal to EF at T greater than 0 Kelvin. At the temperature more than absolute 0, if E equal to EF, what do we get? See, this expression becomes 1 by e power 0 plus 1. The equation becomes e power 0 plus 1 equal to F. This is 0. 0 plus 1, so then we get f of E equal to half. What do you observe here? At the energy E equal to EF. That's not EF of 0. In that case, E equal to EF. The probability of filling the states is half. That particular level having energy EF is half filled. This is how this graph explains the probability of filling the different energy states. And using these things, let us derive the expression for Fermi energy at absolute 0. And let us see how this quantum free electron theory explains the facts which are not explained by classical theory. Let us consider that one in the next class. So, I stop here. Thank you.